Antimatter is the exact opposite charged twin of every particle inside your body, and it is the most efficient destroyer. A bomb burns fuel and wastes most of its mass as leftover ash. Antimatter wastes nothing. Every scrap of mass on both sides converts into pure light at 100% efficiency, following the oldest and simplest equation in modern physics. The universe should not have allowed you to exist to hear it. In the first violent instant after the Big Bang, physics demands that matter and its antimatter twin were created in exactly equal amounts. Instead, there is a planet under your feet, a body around your thoughts, a species that built telescopes and cathedrals. Over the next hour, you will travel through the discovery of antimatter before anyone believed it could exist, the annihilation event that outperforms every weapon ever built, the almost impossibly small numerical accident that let anything survive at all, and the underground magnetic traps at CERN where scientists now hold antimatter still, like a splinter of the world that was never supposed to be here. If wonder like this is what keeps you up at night, take a moment to like and subscribe. It is a measured, catalogued, laboratory-confirmed object with its own mass, its own spin. The only difference between a particle and its antiparticle is charge flipped exactly as if someone had taken the blueprint for an electron. Your body is built from electrons, each carrying a negative charge. The mirror twin of the electron is called the positron, and it is identical to the electron in every measurable way, except that its charge is positive. Same mass, to a precision physicists have checked obsessively for a century, looking for even the smallest asymmetry that might explain why you exist. A positron falls into the same orbital patterns, obeys the same quantum rules, and reacts to electric and magnetic fields in the mirror-inverted way. It is not a reverse particle in some vague, poetic sense. It is a specific object, made in specific machines, tracked on specific instruments, and it has been part of confirmed physics since the early 20th century. Protons have an antiparticle too, called the antiproton, negatively charged where the proton is positive, and neutrons, despite having no charge to flip, have their own antimatter version distinguished by an internal quantum property called baryon number, flipped to the opposite sign. Quarks have antiquark. Neutrinos, the ghost particles that pass through your body by the trillions every second without you feeling a thing, because it may be the key to everything else in this story. For now, hold on to the basic shape of the idea. Every known matter particle appears to have a shadow version with the same mass and opposite charge. And if you brought one specimen of each together, they would not coexist. What makes this stranger than it first sounds is that nobody stumbled onto antimatter by accident, the way many discoveries in physics happen. It was demanded by mathematics first, years before a single antiparticle had ever been detected by any instrument on Earth. He wanted an equation that described the electron in a way that satisfied both quantum mechanics and Einstein's special relativity at the same time. Two frameworks. What he produced, the equation that now bears his name, worked beautifully. It correctly predicted the electron's behavior, its spin, its magnetic properties, all of it with an elegance that still strikes physicists today as almost suspiciously. But the equation had a second set of solutions that Dirac could not get rid of mathematically. For every positive energy solution describing an ordinary electron, there was a matching negative energy solution and negative energy in the framework. A particle should not be able to have less than zero energy and still exist as a stable physical thing. Dirac's first instinct was to treat those negative energy solutions as a mathematical artifact, an unwanted leftover to be explained away or ignored, the kind of thing physicists sometimes do. But Dirac did not ignore it. He took the strange solution seriously, the way a good detective takes seriously a clue. He suggested that these negative energy states corresponded to real particles and that what you perceive as empty space is actually a sea. Occasionally, he reasoned, enough energy might strike this sea and knock one of the negative energy particles out of it, leaving behind a hole. At first, Dirac speculated that this hole might be the proton, the only other charged particle known at the time, since physicists are naturally reluctant to invent an entirely new object if an existing one might do the job. But the mathematics did not cooperate. A hole in his negative energy sea had to have the same mass as the electron. That mismatch would not go away no matter how the equations were rearranged, and by 1931, Dirac accepted the uncomfortable conclusion, his own theory. There had to be a new particle, unseen by any instrument on Earth, with the mass of an electron and a positive charge. He called it, tentatively, the anti-electron, and he published the idea in a physics journal, fully aware that he was asking the world. It gets stranger, because within about a year, someone found it. In 1932, an American physicist named Carl Anderson was studying cosmic rays, the constant rain of high-energy particles that strikes the Earth's atmosphere from space. A cloud chamber is a sealed container of supersaturated vapor. When a charged particle passes through it, it leaves a thin, visible trail of condensation, the way a jet leaves a contrail across the sky. And by placing the chamber inside a strong magnetic field, Anderson could bend those trails and read off the particle's charge and momentum from the curve. Negative particles curved one way, positive particles curved the other. It was, in effect, a way of photographing On August 2nd of that year, Anderson photographed a track that curved the wrong way for an electron but matched an electron's mass. At first, the simplest explanation, the one that requires inventing nothing new, would have been a proton moving in the opposite direction. Protons are positively charged, after all, and would curve the same direction as a positive electron. But Anderson had placed a lead plate across the middle of his chamber, specifically to settle this kind of ambiguity. A particle loses energy passing through lead, so its curve becomes tighter on the far side of the plate. And by measuring exactly how much tighter, Anderson could calculate the particle's mass. The particle in his photograph curved before the plate and curved more sharply after it in a way that was consistent with a particle roughly 2,000 times lighter. And it curved like a positive charge. He had found Dirac's anti-electron sitting in a photographic plate 4 years after it had first appeared as an inconvenient extra term in an equation nobody wanted. Anderson named the particle the positron, and the discovery was confirmed within months by other physicists working independently, including a research group in Britain that had, unbeknownst to Anderson at the time, already captured similar tracks without recognizing what they were looking at. Anderson received the Nobel Prize in Physics in 1936 at the age of 31, one of the youngest laureates in the prize's history for finding, embedded in the ordinary rain of cosmic particles falling on Earth every single day, an object that theoretical mathematics had insisted must exist. Here is what makes that discovery matter beyond the history books. It was not an isolated curiosity. It was proof of a pattern that has held ever since in every particle accelerator built in the century that followed. Wherever physicists have looked for antimatter with sufficient energy and sufficient precision, they have found it exactly. The antiproton was confirmed in 1955 at the Bevatron accelerator in Berkeley. The antineutron followed within a year. It is a routine byproduct, generated constantly in industrial quantities by machines built specifically to smash matter together hard enough to conjure both a particle and its shadow twin. The pattern Dirac's equation, revealed in 1928, has never once broken. Every particle physicists have ever definitively confirmed has an antimatter partner, without exception, and the confidence in that symmetry runs so deep that when physicists talk about the part of the universe that does not follow it, they do not talk about it. They talk about it as one of the deepest open wounds in modern physics. That wound is the reason this story exists at all. And to understand it, you first need to understand exactly what happens when matter meets its twin, because the scale of that reaction is what makes the missing antimatter such an unbearable question. Picture the most efficient furnace you can imagine, one that converts fuel into energy with zero waste. There is no such furnace anywhere on Earth, because every chemical reaction, every combustion engine, every star converts only a tiny fraction. A star, like the Sun, at its core, fuses hydrogen into helium and converts only about 0.7% of the mass involved into energy. Even a nuclear weapon, the most concentrated release of energy humanity has ever engineered, converts less than 1% of its fissile material's mass directly into energy. The remaining material is still there afterward, transformed, radioactive, dangerous, but still matter. Antimatter annihilation does not work like that. When a particle meets its antiparticle, the entire mass of both, 100%, converts directly into energy, according to Einstein's equation. No ash, no residue, no leftover nucleus. The two particles do not merely collide the way two billiard balls collide and bounce apart. They cease to exist as matter altogether and reappear in that same instant as pure electromagnetic radiation, typically it is the cleanest, most complete conversion of mass into energy that the laws of physics allow anywhere in the universe, and it happens instantly. To make that abstract number feel physical, consider what a single gram of antimatter meeting a single gram of ordinary matter. Run it through Einstein's equation, and the 2 grams combined, colliding completely, would release energy on the order of 43 kilotons, in the same general range as a modest nuclear weapon. Scale that up to a kilogram of antimatter, roughly the mass of a liter bottle of water, and the resulting explosion would rival the largest nuclear detonation ever tested, released from material with no fissile core, no chain reaction, no critical mass requirement. It simply needs contact. This is why antimatter, when science fiction reaches for the most extreme possible energy source imaginable, keeps returning to it, gram for gram. Nothing else in known physics comes close. That efficiency is exactly why serious engineers, not just science fiction writers, NASA's Institute for Advanced Concepts, funded early feasibility studies into antimatter catalyzed propulsion in the 1990 seconds. The appeal is the same efficiency that makes antimatter terrifying at larger scales. No chemical rocket fuel, no fission reactor converts anywhere near this fraction of its mass directly into usable energy. The obstacle in every serious proposal has never been the physics of the reaction itself. It has been production. Producing antimatter in particle accelerators today is staggeringly inefficient and staggeringly expensive, requiring enormous energy input to create even nanogram quantities, where scientists hold a comparative handful of anti-hydrogen atoms suspended, never touching in a vacuum. No spacecraft has ever flown on antimatter fuel, and none is close to doing so, but the theoretical energy density remains on paper unmatched by anything else physics currently allows, which tells you something important about the scale of what was fighting for survival in the first instant after the Big Bang. And this is precisely why the birth of the universe should have been the most violent, complete, and total act of self-destruction. At temperatures and densities that make a nuclear weapon look like a struck match. Here is the part that matters. The equations that govern particle physics, the same equations confirmed again and again by every collider experiment ever run, predict that matter. This is not a guess. It is baked into the deepest structure of the theory, tested at every energy scale physicists have ever reached. Smash particles together in an accelerator today at any energy, and you get matter and antimatter in pairs symmetrically every time. There is no known process confirmed in any laboratory that manufactures a meaningful excess of one over the other. Apply that same rule to the first instant of the universe, when unimaginable energy was condensing into the first particles of matter. And the conclusion is unavoidable. Equal parts matter, equal parts antimatter, flooding into existence together. And because matter and antimatter annihilate on contact with total efficiency, as you now understand, that first fraction of a second, every particle finding its antiparticle, every antiparticle finding its particle, the entire content of the infant universe converting itself back into a blaze of photons. No stars, because there would be no matter left to gather into them. No planets, no chemistry, no you. This is called the baryon asymmetry problem. It is treated by the physics community as one of the central unsolved questions in cosmology, sitting alongside dark matter and dark energy as a gap in the standard model that everyone acknowledges. The universe you inhabit is direct physical proof that the annihilation was not total. Somehow, somewhere, in that first second, a residue of matter survived without a matching antiparticle. Every galaxy, every star, every atom in the chair you may be sitting in, and the body you are sitting in it. For roughly every billion antimatter particles created in the early universe, there were 1,000,000,001 matter particles, not a billion, out of every billion matched pairs, annihilating instantly and converting to light. A single solitary extra particle of matter was left standing with no partner. Every living thing that has ever existed anywhere. Try to hold the scale of that number honestly. If you had $1 billion in cash, spent every single one of those dollars completely, and were left with exactly one extra dollar bill in your pocket, at the end, that stray dollar is not a rough analogy for the survival of matter. It is closer to a description of a rounding error in an accounting system so vast it beggars description. And yet that error is the only reason there is a you to imagine holding the dollar in the first. You are not made of the substance of the universe in any average sense. You are made of the residue, the single line item that failed to cancel out in the largest ledger ever balanced. Cosmic annihilation on a scale of 1,000,000,000 to 1. This is not a number physicists simply assumed or estimated loosely. It comes from two independent lines of measurement that agree with each other to a remarkable degree, which is exactly the kind of agreement that makes a physicist take a number seriously. The first comes from counting directly the ratio of photons to ordinary matter particles left over in the universe today, a ratio preserved almost perfectly since the era of annihilation, because photons barely interact with anything as the universe expands and cools. The second, entirely independent line of evidence comes from the afterglow of the Big Bang itself, the cosmic microwave background, mapped in extraordinary detail by satellites, including the tiny temperature variations imprinted across that afterglow encode, among many other things, exactly how much ordinary matter existed in the early universe. Two separate methods built on entirely different physics, converging on the same tiny number. No confirmed theory in physics fully explains why that error happened, why the ledger did not balance perfectly, why the universe did not do what its own equations say it should have done. There are candidate explanations which this story will walk through later, and none of them has been proven. What is proven beyond any reasonable doubt, what has been measured, confirmed, and cross-checked by independent experiments for decades, is the scale of the number itself. One extra particle of matter for every billion perfectly matched, perfectly annihilating pairs. That is the margin the entire visible universe survived on. It gets stranger from here because physicists have found something that comes tantalizingly close to explaining a piece of that imbalance, and it very nearly convinced an entire generation of scientists that the mystery was solved. In 1964, at Brookhaven National Laboratory on Long Island, two physicists named James Cronin and Val Fitch were studying a strange, short-lived particle called the neutral kaon, and in the process they found the first confirmed crack in a symmetry that physicists had assumed. Up to that point, the symmetry in question combines two ideas: charge conjugation, which swaps particles for antiparticles, and parity. Combined, physicists call this CP symmetry, and the assumption before 1964 was that the laws of physics should look identical whether you swap every particle for its antiparticle, mirror the whole system. Nature, in other words, should not be able to tell the difference between a universe and its antimatter mirror image. Cronin and Fitch found that neutral kaons decay in a way that very slightly. The decay rates were not perfectly symmetric between the matter and antimatter versions of the process. It was an extraordinarily small effect, measured in fractions of a percent, but it was real, it was reproducible, and it meant that somewhere in the deep structure of physics, nature has a very faint preference, a thumb ever so slightly, on the scale favoring matter over antimatter in certain rare interactions. Cronin and Fitch received the Nobel Prize in Physics in 1980 for the discovery, and CP violation, as physicists now call it, immediately became one of the most closely studied phenomena in particle physics, because it was. Here is what makes this genuinely unsettling rather than simply interesting. In 1967, a Soviet physicist named Andrei Sakharov, better known to most of the world for his later work in nuclear arms control and human rights, CP violation was one of his 3 required conditions. Without some process that treats matter and antimatter asymmetrically. There is no mechanism by which one could ever end up more abundant than the other, no matter what else happens. Cronin and Fitch had found exactly that kind of process, seemingly right on schedule for the discovery physics needed. For a while, some physicists hoped this was the answer. Not a full stop, an actual explanation that the CP violation observed in kaon decay might, once you ran the numbers across the enormous timescales and temperatures of the early universe. The hope did not survive contact with arithmetic. When physicists calculated exactly how much matter-antimatter asymmetry the known CP violation from kaons could actually generate, the number came out staggeringly small, many orders of magnitude too small to account for the imbalance the universe actually needed. The effect Cronin and Fitch discovered was real, confirmed, and Nobel-worthy, and it is simply not big enough. Physicists did not stop looking. In 2019, the LHCb experiment at CERN, one of the 4 major detectors ringing the Large Hadron Collider, announced the first confirmed observation of CP violation in a different family of particles entirely, baryons built from charm quarks. It was the first time CP violation had been confirmed outside the kaon, and later the B-meson systems where it had previously been observed, and it strengthened physicists' confidence that this asymmetric quirk of nature is not a one-off oddity restricted to a single strange particle. It appears in smaller or larger degrees across multiple families of matter, but confirming that the effect shows up in more places did not solve the scale problem. Every confirmed instance of CP violation measured so far across kaons, B-mesons, and now charm baryons, so physicists are left holding a genuine Nobel Prize confirmed piece of the puzzle that is nowhere near large enough to complete the picture. That preference is confirmed, repeated, and expanding into new particle families as detectors improve. and it is still by a staggering margin. Somewhere, there must be a far larger source of that asymmetry operating at energies or in particles physicists have not yet directly observed. That gap between the CP violation that is confirmed and the CP violation that is required is one of the starkest unresolved numbers in modern cosmology, and it sits quietly underneath every star you have ever looked up at. Here is the part that makes this personal, not abstract. Right now, inside your own body, atoms of potassium are quietly producing Potassium is an essential element for your nervous system and your muscles, including the muscle of your heart, and a small constant fraction of the potassium in a fixed and unavoidable proportion that comes from the food you eat. Bananas are famous for containing it, which is why physicists sometimes half-jokingly measure small amounts of radiation in banana equivalent doses. It is in potatoes, in leafy greens, in meat, in you, structurally inseparable from ordinary dietary potassium, because it is chemically identical, just a slightly heavier. About 11% of the time potassium-40 decays. It does so through a process called positive beta decay, in which the nucleus emits a positron, the very same antimatter particle Carl Anderson photographed in 1932. That positron does not travel far. Within a fraction of a millimeter of being created, somewhere inside your own tissue, it encounters an ordinary electron, and the two annihilate exactly the way you would expect, converting their combined mass instantly into two gamma-ray photons that fly outward in opposite directions. This is not a rare or exotic event. It happens inside the average adult human body on the order of several hundred times every single day. A continuous, low-level drizzle of antimatter annihilation occurring quietly inside your bones and your muscles, entirely invisible, entirely harmless at this scale, and entirely real. You are not a passive bystander to the story of antimatter. You are, in a small but genuine sense, an active participant in it, a warm-blooded site of matter-antimatter annihilation happening on a biological clock. Right now, scientists have measured this precisely enough to use it as a kind of natural calibration tool, and it also means that when physicists talk about antimatter, it also belongs to your dinner plate, your skeleton, and the ordinary background radioactivity of the biosphere you were born into. The mirror twin particle predicted by an abstract equation in 1928 and photographed in a cloud chamber in 1932 is manufacturing itself in small quantities inside you continuously as an ordinary and unremarkable biological fact. But knowing that antimatter forms constantly and briefly in trace amounts inside living tissue is a very different problem than capturing it. Antimatter cannot simply be placed in a container because there is no container made of matter that antimatter will not annihilate against on contact. A jar made of glass, a chamber made of steel, even the thinnest possible physical wall, all of it is ordinary matter, and antimatter, touching any of it, disappears instantly, in a flash. If physicists want to study antimatter for longer than a fleeting instant, they have to hold it without ever letting it touch anything solid, suspended entirely by invisible forces, which is precisely the challenge the Alpha experiment at CERN. Alpha does not trap antimatter in a jar. It traps antihydrogen, the antimatter equivalent of the simplest atom in the universe, a single antiproton orbited by a single positron. Never touching any physical surface. Producing the antihydrogen in the first place requires slowing down antiprotons, created in high-energy collisions, down to temperatures near absolute zero, cold enough that they move slowly enough to be caught, and then carefully combining them with equally cold positrons, so that they bind together into atoms. Every step of this process fights against the same underlying problem. The moment antimatter touches anything at all, the Alpha collaboration first successfully trapped antihydrogen atoms for a meaningful length of time in 2010, holding a small number of them in their magnetic bottle. Within a year, the same team extended that confinement to over 16 minutes, long enough to begin doing actual spectroscopy, actual measurement of antihydrogen's internal structure, comparing it directly against ordinary hydrogen. Every measurement so far has found antihydrogen behaving exactly the way the standard model predicts it should, a mirror image of hydrogen. It is so far a perfect twin, offering no hint, no crack, no asymmetry that might explain why one twin dominates the universe. That perfect symmetry raised a question that sounds almost childishly simple, and yet had gone unanswered by direct experiment for the better part of a century. Does antimatter fall down the way everything else in your experience falls down, or does it fall up? It is a question that could only be asked seriously once physicists had learned to trap antihydrogen long enough to actually drop it and watch, and the honest answer, for decades, and any gravitational effect on a handful of individual antihydrogen atoms is swamped almost instantly by the comparatively enormous electric and magnetic forces. You cannot simply open a magnetic bottle and watch antimatter drift downward under gravity when the residual magnetic fields in the apparatus are millions of times stronger than gravity's pull. For a long time, this remained one of the most basic unanswered questions about antimatter, a gap that theorists filled with speculation. Some serious physicists, including a minority working through modified theories of gravity, floated the idea that antimatter might actually experience anti-gravity. If true, it would have rewritten fundamental physics from the ground up. Here, is what makes that a genuinely thrilling question rather than an idle one. If antimatter fell upward, it would not simply be a curiosity about a rare laboratory substance. It would mean gravity itself does not behave as Einstein's general relativity says it should, because general relativity predicts unambiguously. An upward falling anti-hydrogen atom would have been one of the most significant experimental results in the history of physics. To settle it, the Alpha collaboration built a dedicated successor experiment called Alpha G, engineered specifically to test gravity's effect on trapped antihydrogen. The design used a vertically oriented magnetic trap, releasing antihydrogen atoms gently and tracking with extraordinary care which direction they moved. In 2023, the Alpha G team published their result. Antihydrogen falls down. Not sideways, not up, but down, consistent with ordinary gravity within the uncertainties their apparatus could measure, matching the prediction of general relativity. It gets stranger in a quieter way once you sit with what that result actually means. This was, genuinely, one beautiful, a question that had lingered unanswered by direct observation. Since Dirac's era finally had a definitive experimental answer, and the answer turned out to be the boring one, the one general relativity. No anti-gravity, no exotic new force. Gravity does not care whether the mass beneath it is matter or antimatter, and it treats both exactly the same. For a story built entirely around unsolved mysteries, it is worth pausing on this one, because it is proof of how this entire field actually works. Physicists build extraordinarily delicate machines, ask a precise question nature had never been asked directly before, and sometimes nature answers cleanly, and the universe turns out to be a little less strange and a little more consistent than the wildest guesses feared. The gravity question is closed, but closing it did nothing to touch the far larger mystery still sitting underneath everything else in this story, the 1 in a billion asymmetry that let matter survive at all. Whatever tipped the scale toward matter in the first fraction of a second after the Big Bang, it was not a difference in how gravity pulls on the two forms of mass. That answer is closed and shut firmly, and the deeper question waits exactly where it was before the experiment began. Here is the part that matters most for you. Antimatter is not confined to a mystery locked away in an underground tunnel in Switzerland. It is at this moment, quite possibly inside a hospital near you, being used to save someone's life. Positron emission tomography, the medical imaging technique doctors call a PET scan, is built entirely on the physics of antimatter annihilation, deployed as a diagnostic tool rather than a subject of pure research. A patient undergoing a PET scan is injected with a mildly radioactive tracer, a molecule, often a sugar analog, tagged with an isotope. Cancerous tumors, among other tissues, tend to consume glucose at a much higher rate than healthy tissue, so the tracer concentrates preferentially. As the isotope decays, it emits positrons which travel a short distance through tissue before annihilating with an ordinary electron, exactly as described earlier in this story. A ring of detectors surrounding the patient catches these paired photons, and because they are emitted simultaneously and in opposite directions, do this for millions of individual annihilation events over the course of a scan, and the result is a detailed, three-dimensional map of exactly where in the body's cellular activity. Inside a human body, dozens of times, every single day, in hospitals around the world. What began as an abstract mathematical embarrassment in Dirac's equation, an unwanted negative energy term he initially wanted to discard, has become one of modern medicine's most valuable diagnostic technologies, quietly saving lives using the same annihilation event that scaled up by a factor of trillions. Everything in this story so far has assumed something that sounds obvious, but has never actually been proven beyond doubt, that the entire observable universe is made overwhelmingly of matter, with only trace, transient antimatter appearing briefly in radioactive decay, cosmic ray collisions. Before annihilating and vanishing again. But there is a genuinely open question lurking underneath that assumption. What if that is only true of the neighborhood you happen to live in? What if, somewhere far enough away, in some region of the universe, never yet observed in enough detail, entire galaxies of antimatter survived, instead of matter, mirror pockets of the cosmos, where every star is built of antiprotons, because antimatter stars would shine with ordinary light, obeying the same physics, giving off the same spectra. This is not idle speculation. It is a testable hypothesis, and one experiment has been hunting for the answer from orbit for over a decade. The alpha magnetic spectrometer, known as AMS-02, is mounted on the exterior of the International Space Station, where it has operated continuously. Among the trillions of particles AMS-02 has recorded, scientists are searching patiently and specifically for anti-helium nuclei. The logic behind the search is precise. Individual antiprotons and positrons are created constantly throughout the universe by entirely ordinary, well-understood processes, high-energy cosmic ray collisions striking interstellar gas, for instance. So, finding stray antiprotons in space proves nothing new. But anti-helium is different. Helium nuclei do not form easily from random collisions. They require the kind of sustained, high-pressure fusion that only happens inside the cores of stars or in the earliest moments of the universe's formation. If AMS-02 detected even a single confirmed anti-helium nucleus arriving from deep space, it would be extraordinarily difficult to explain through ordinary cosmic ray physics, and it would point toward something genuinely new, an actual antimatter star, or an antimatter-dominated cluster of galaxies, somewhere out there producing it through fusion, the same way ordinary helium is produced inside the Sun. So far, across more than a decade of continuous data collection, spanning well over 100 billion detected cosmic ray events, a handful of ambiguous anti-helium-like signals have appeared in the data over the years. Candidate events that briefly excited the collaboration, more likely explained as instrumental background or misidentified ordinary particles than as genuine antimatter arriving from a distant antimatter galaxy. The instrument is still operating, still recording, still watching every single cosmic ray that happens to strike it from any direction in the sky, because a single confirmed anti-helium nucleus would be one of the most significant discoveries in the history of astrophysics, and the absence of one, so far, is itself a meaningful piece of evidence. Quietly narrowing down how much antimatter, if any, could still be hiding somewhere in the observable universe waiting to be found. None of this, the trapped antihydrogen, the CP violation experiments, the potassium in your bones, the search from orbit. Here is the part that matters, because physicists do have candidate answers, genuine mathematically serious proposals developed by serious researchers. The leading family of ideas goes by the name leptogenesis. The rough proposal is that extremely heavy hypothetical particles called sterile neutrinos, far more massive than any neutrino physicists have, which include electrons and neutrinos over their antimatter counterparts. That initial small imbalance, the theory proposes, could then have been converted through a separate and equally exotic process involving the weak nuclear force into the baryon asymmetry you have been learning about this entire time. It is an elegant idea, mathematically consistent and taken seriously by a large portion of the theoretical physics community, and it is, as of today, sterile neutrinos, if they exist at all, have never been directly detected in any laboratory. Their proposed mass sits so far beyond what any collider on Earth has ever reached that testing the theory directly, rather than simply arguing that it is mathematically plausible, physicists believe leptogenesis is a promising direction. Some consider it the leading candidate explanation available today. Other proposals exist alongside it, involving even more exotic physics beyond the standard model. Every one of them remains a hypothesis competing for evidence that does not yet exist. There is one further thread worth knowing, because it shows how seriously physicists are pursuing an actual test of this idea, rather than leaving it as pure theory. If neutrinos are their own antiparticles, a property physicists call being Majorana particles, distinct from every other known matter particle. Permitting the lepton asymmetry the theory requires. Several major underground experiments, including detectors buried deep beneath mountains in Italy and in former mine shafts in the United States and Canada, are searching for an extremely rare hypothetical process. If any of these experiments ever confirms that process, it would not prove leptogenesis outright, but it would remove one of the largest remaining. As of today, after years of increasingly sensitive searches, none of them has found it. The neutrino's true nature, matter, antimatter, or something that blurs the line between the two, remains unconfirmed, and with it, so the honest state of the field, after nearly a full century of confirmed antimatter physics from Dirac's 1928 equation, every piece of the puzzle physicists have actually confirmed, put together, adds up to only a small fraction of the asymmetry the universe actually needed. The rest, the vast majority of the reason you exist at all, remains an open question, actively researched, seriously debated, and entirely. Here is the part that turns this from a puzzle about particle counts into something closer to a theoretical reflection on how improbable your existence This is not a claim about danger, and it is not a warning about anything that might happen to you or to the universe going forward. The asymmetry that produced matter was locked in, one way or another, in the first fraction of a second after the Big Bang, and whatever tipped that scale has already happened, irreversibly, roughly 13.8 billion years ago. What follows is simply an exercise in imagining the other ways the dice could have landed, because physicists who study this question have run exactly that exercise. Imagine first that the asymmetry had been precisely zero, no leftover matter at all. A universe where every single particle found its antiparticle in that first violent instant, and the entire content of everything converted completely. In that universe, and physicists can describe its properties with some confidence because the underlying physics is forever. No observer would ever exist within that universe to notice its own emptiness, because observers require matter, structure, complexity, chemistry, and a universe with a perfectly balanced ledger has none of those things to offer. It is, in a very literal sense, the most likely outcome the raw mathematics of particle physics predicts, and it is the outcome Now imagine the asymmetry tipped in the other direction, favoring antimatter instead of matter by that same 1 in a billion margin. Physicists are careful to point out that this version of the universe would, as far as anyone can tell, look essentially identical to the one. A universe built from antimatter instead of matter would still form antimatter stars antimatter planets, and plausibly antimatter chemistry complex enough to support antimatter versions of biology, indistinguishable in its internal experience from the universe you actually because the laws of physics treat both symmetrically apart from that faint CP-violating preference. The interesting case, the one that keeps theorists up at night, is not matter versus almost any small, non-zero tip of that scale in either direction produces a universe with structure, and the exactly zero outcome. That reframes the fine-tuning question in an interesting way, and it is worth stating clearly because it would be easy to walk away from this story. The truly narrow, terrifying knife edge is not the specific direction the asymmetry took. It is the fact that there was any asymmetry at all, rather than the perfectly balanced, perfectly symmetric outcome the underlying particle physics seems. Every confirmed source of that asymmetry that physicists have found so far, the CP violation in kaons, in B mesons, in charm baryons, is real but too small by many orders of magnitude to have produced the 1 in a billion excess. Something else, some mechanism still unconfirmed, whether leptogenesis, whether an undiscovered symmetry-breaking process in the early universe, whether something no physicist has yet proposed pushed that scale away from perfect balance and toward the existence of matter, and by extension, toward the eventual existence of you. Sit with that for a moment, honestly, without either dismissing it or inflating it into something more dramatic than the science supports. You are not the necessary, inevitable outcome of the laws of physics operating the way they are expected, left entirely to their own confirmed devices, without whatever additional, still unidentified mechanism intervened in that first second. Those laws predict total, permanent, structureless emptiness, a universe that annihilated itself completely and left behind nothing but cooling light. Something interrupted that outcome. And the interruption succeeded so narrowly by 1 part in a billion that reasonable physicists describe the resulting universe, the one containing planets and telescopes and the sound of your own thoughts, as a kind of statistical anomaly riding on the back of an error term nobody has fully explained. It gets stranger because this same fine-tuning logic surfaces again and again throughout physics, in the precise strength of the forces that bind atomic nuclei together, in the precise rate of the universe's expansion, in dozens of independent numbers. Would have produced a universe incapable of forming stars, chemistry, or observers of any kind. The baryon asymmetry is simply the earliest, and in some ways the starkest entry on that list, because it operated before atoms existed, before stars existed, before there was anything at all except a violent, self-annihilating soup of matter and antimatter deciding by the thinnest possible margin. None of this is a warning. Nothing is at risk today because of a decision the universe made in its first second nearly 14 billion years ago. It is simply the quiet, permanent fact sitting underneath your past, underneath every moment you have ever lived, underneath every person you have ever loved. Everything solid you have ever touched, the metal of a doorknob, the ground beneath your feet, the bones inside your own hand, is the surviving residue of a war the universe fought against itself in the first fraction of a second of its existence. Not a war between good and evil, not a war with a villain or a victor deserving credit, but a war of pure physics. Empty light expanding forever with nothing left inside it to ever notice the emptiness. Instead, by a margin of 1 part in a billion, so small that if you tried to represent it physically, you would need a number more precise than almost anything else measured in science. That survival became hydrogen. Hydrogen gathered under gravity into the first stars. Stars forged heavier elements in their cores. Those elements became planets, oceans, chemistry, and eventually, on at least one small world, orbiting an unremarkable star, something complex enough to ask the question you have been listening to for the past hour: why is there something rather than nothing? Physicists have gotten remarkably far in explaining what antimatter is, how it behaves, how it is trapped, how it is used, how it can be detected, pouring quietly out of your own bones. They have not yet closed the gap between the tiny asymmetries they have confirmed in the laboratory and the vastly larger asymmetry the universe actually required to leave anything behind at all. It is the frontier of it, an open door that CERN and AMSO2 in orbit, and the next generation of particle colliders not yet built are still walking through. What are you made of? And why? Against every likelihood, the mathematics predicts, were you ever made at all? Stay curious.